So in this lecture, we're going to talk about vectors. So recall from the flipped class videos, our vectors from that video were quantities that have a magnitude and a direction. So suppose I walk east for 1 mile, right? So this gives me a vector. This has a magnitude, 1 mile, and it has a direction, which is we're going to walk east. So we can represent this as this vector, say we'll write it as v. So we put an arrow over it when we're drawing it at the board or on this tablet here. I'll bold it when you saw it was bolded in the flipped class video. So now I can represent this as an arrow going like this if I choose east to be to the right of the screen here. We could also walk in the other direction as well. If we walk 1 mile west, well, this has this same magnitude, but the exact opposite direction. So it would look something like this. And we can go ahead and call this vector, we're going to denote this as negative v, because notice if I walked 1 mile east and then 1 mile west, I'd be exactly where I started, so I wouldn't have moved anywhere. So it makes sense to call this negative v. And similarly, if I went 2 miles east, well, that would be in the same direction but longer. So I could think of this as the vector v, and then the vector v again. So we're going to call this vector 2v, because we've stretched the distance from 1 to 2. So we've basically scaled our vector by 2. So now, let's suppose I walk 2 miles east and then 3 miles south. Now, I could think of this as first I walk 2 miles east, so let's call this vector, say, u, and then I walk 3 miles south. Maybe make that a little longer, so call this w. So we can position these vectors wherever we want. So I position my south vector at the tip of my u because I'm going to walk east and then south. So then I can go ahead and connect these vectors to see where did I actually walk. In this connection vector here, we're going to call this u plus w. So we do u and then we do w. And we can see we could also have done the other way. If we would have walked south first with the w and then east with u, notice the vector I get when I add these two is the exact same vector. So this would be w plus u, and we can see here these are if we look at the two blue vectors, those are the same vector. So u plus w is the same as w plus u. It doesn't matter whether you walk east and then south or whether you walk south and then east. So that shows us how we can add the vectors together. Now, in the flipped class video, it was mentioned that we don't keep track of where the vectors are. The vectors can be anywhere, so you can move vectors all over the place, and it's the same vector, right? So if I draw v here like this, and then I draw v down here, as long as it has the same magnitude in the same direction, it's the same vector. But sometimes it is useful to put the vectors in a coordinate space. So suppose I do want to work in the xy plane, just to make things a little easier on myself. Well, there's two very important vectors that we can kind of build every other vector from for this. So the first vector is this vector that just points one unit in the x direction. So this vector here, this is I, and we're going to put a hat over it instead of an arrow because it has length 1. The other vector is going to go just in the j direction, or in the y direction. We're going to call this vector j. So in general, if a vector has length 1, so this means length or magnitude, we'll get back to that in a bit, we call it a unit vector. And I'll usually write it then with a hat over it instead of an arrow, just to keep track of the fact that it's a unit vector. So now back to our vectors I and j here. Notice that the I goes one direction in the x and 0 directions in the j, so we could write this as a 1, 0. 1 in the x direction, 0 in the y direction. And j is the opposite, it goes 0 in the x and 1 in the y. So we can represent with these two brackets here. And as I mentioned, we can take any vector and write it in terms of these two vectors. So let's see how that works. So let's let v be some vector, and we'll draw this vector here in the xy plane. And we'll center our vector at the origin. Like I said, we can put the vectors anywhere, but for us it's going to make it easier here to put this at the origin. And let's suppose it goes a units in this direction and b units in the y direction. So what we could see then is if I were to take the vector I and scale it by a, that would go all the way out to here. So this vector here would be ai. And then if I take j and scale it by b, that would be this vector here. So we see that v is actually ai plus bj. And we could also write this, if we want to use the brackets notation, like this. It doesn't matter whether you use I and j or brackets. I'll go back and forth with them. So that's how we can represent any vector in terms of these two, what they're called basis vectors, I and j. We saw before we can scale a vector, and that changes the length of the vector. So in this case, that just multiplies both of our terms by that scalar. So we'd also like to be able to add vectors in terms of these coordinates. So if, say, v is this vector AB and w is equal to CD, what is v plus w in the coordinates? Well, we can figure this out by drawing pictures here. So let's start just by illustrating our vectors here. So let's say I have v here, this is AB, and then maybe w looks like this, and this is CD. Now remember, we can place these vectors wherever we like. So let's move the vectors and reposition. So let's leave v where it is. So this is v. So I know this distance here is b, and this distance is a. And now let's take w and let's place it at the end of the vector here. This is w. So I know this distance here is c, and this distance here is d. So now if I connect these vectors, to get the addition, so this vector is v plus w. Notice the x-coordinate of that is going to be a plus c, and the y-coordinate of that is going to be b plus d. So to get the addition of two vectors, sorry, that's a terrible color, I won't use that one again. To get the addition of two vectors, we just add the components together. So we can also think of this in terms of the i's and j's. then b plus w. This is ai plus bj plus ci plus dj, and we just add the components. So the coefficients of the i's add together, and the coefficients of the j's add together. And that's how we add the vectors. So we can also consider subtraction. So if I have the vectors in this case, let's again think about our vector v here and our vector w. Well, there's two ways to do what would v minus w look like. One thing we could do is we could take negative w, so that's negative w would look like this, and we can add that to v. So this would be negative w. So we could put that at the tip here, and then notice my new vector would be something like this. So this would be v, really it's plus minus w, which is v minus w. So that's one way to do it. Another way is we can just use the vectors themselves to do this. So if I have v here, and let's go back to get w again. The other way I can think of this is what should v minus w be? This should be the vector so that when I add w, I get v. So in that case, if I add whatever this is to w, I should get v. So that tells me exactly, not the most intuitive way to do this, but it is the fastest way in terms of drawing. It should be this vector here, which you can see matches up exactly with the vector we did when we did the minus w, or the v plus minus, plus the negative of w. So v minus w connects the end of w to the end of v. In terms of coordinates, well, we know if we think of it the first way, v minus w is the same as v plus negative w. So this is ab plus negative c negative d. So this is a minus c, b minus d. So it just do the computation inside the coordinates like we did for addition. Okay, so I also mentioned the magnitude of the vectors above, and so we can also write the magnitude. If we have the vector in terms of coordinates, we can do the magnitude in terms of the coordinates as well. So if I have my vector v here, and suppose v is ab again, so that means this distance here is a, this distance here is b. So then the magnitude of v, well, we can just use Pythagorean theorem, so this should be square root of a squared plus b squared. So these are kind of our most basic operations on vectors. We're eventually going to move out of 2 space and into 3 space and higher, but these are our most basic ones for 2 space. So let's go ahead and see some examples of how we can use some of this and come up with some different vectors as well. The vectors are going to be extremely important the rest of the semester because basically what we're going to do the rest of the semester is calculus using vectors, which is how calculus was originally invented. It was invented to do physics, and physics is done with vectors. So, okay, so let's find a vector from the point P. So this is going to be 3, 4. So notice these are parentheses, so this is just a point, not a vector, to the point Q, which is, say, 6, 9. And then let's also find a unit vector in the direction from P to Q. Okay, so two things here. First, we're going to find a vector, and then to find a unit vector in the same direction, we just divide by the length of the vector. So let's draw a picture of what we've got going on here. So we're going to start with our point P here. And so this is at the point 3, 4. And then we're going to have Q over here somewhere. And this is at the point 6, 9. And what I would like is a vector that goes from P to Q. So we can see from this, what I need is I need to go 6 minus 3, which is 3 in the x direction, and I need to go 9 minus 4, which is 5 in the y direction. So my vector, which we'll write PQ with an arrow over it to say we're going from P to Q, should be the vector 6 minus 3i plus 9 minus 4j, which is just 3i plus 5j. So that's my vector from P to Q. And now to find the unit vector, I need to figure out what the length of PQ is. So this is square root of 3 squared plus 5 squared, which is square root of 34. And so my unit vector in this direction is the vector PQ divided by its length, because when we divide by the length now, the length of the new vector here will be 1. So this is just 3i plus 5j over square root of 34. And that gives me my unit vector. So in general, we did this with two particular points, but given points, say x1, y1, and q to be x2, y2, the vector from P to Q, let's say, is given by, you take the coordinates of Q, subtract the coordinates of P. And that gives you your vector from P to Q. Now before we move on to vectors in 3 space, let's just note real quick that if I have a point AB, this gives rise to a vector AB. So a point itself isn't a vector, but you can identify for each point you get a vector. So we go out here to this point AB, and how do we get this vector? Well, it's just taking the vector that starts at the origin and goes out to the point. So this way we can think of vectors as equivalent, like not equivalent, but in one-to-one correspondence with points in R2. So the plane is normally denoted as R2. So we can think of each thing in R2 as giving us a vector as well. So now let's go ahead and see what's happening in 3 space. So for a vector, if we want to put one in 3 space, now we have 3 components to deal with. So now think of putting a point ABC here, and our vector going out from the origin to this V. And now we're A in the I direction, we're B in the J direction, but we need a third direction here. So we're going to denote this vector here, K. So this K is 1 in the Z direction. So we'll say CK, and here we've added this vector 0, 0, 1. And now note, our I and J are still in the X and Y coordinates, but now we do have to write them with 3 coordinates because we're in 3 space. So we use the same notation, and it's just left up to the person looking at it to understand which we're talking about, whether it's 2 space or 3 space. And just like before, for each point, we get a vector by just drawing the vector from the origin to that point. And we can do this for higher degree too. So we can take any Rn, and then our basis vectors in this case will just 1 in the first component, 2, 1 in the second component, and then all zeros and so on. Then 1 in the last component. And then a vector in this case would be like A1, E1 plus AN, EN. And this can be useful. We're not always talking about physics when we're working with vectors. For instance, we could have a bunch of different economic data that we want to put into a vector form. And so we might need more variables than just 3 variables. But for the most part, we're going to stick with 3 variables for this course. You just don't have to do that in general. So let's see an example. So let's let v be the vector 2i plus 3j minus 4k, and w to be the vector minus I minus 2j plus k. So a couple computations we can do. The length of the vector v is, again, we can think of this as the distance from the origin to the point 2, 3 minus 4. So this is going to be 2 squared plus 3 squared plus minus 4 squared. So this is 29. We can add vectors just like before. So this is going to be 2 plus minus 1i plus 3 plus minus 2j plus minus 4 plus 1k. And so I just get an I plus j minus 3k. And of course we can scale vectors in 3 space as well. So this gives me minus 2i minus 4j and then plus 2k. So let's consider another example of how we could use vectors to actually solve word problems. So this will be our last example for this section. Okay, so we've got a boat heading north at 15 kilometers per hour. And this is relative to the water. So the current is moving southeast at 7 kilometers per hour. So for the first thing, let's give a vector Okay, so let's give a vector representing the actual movement of the boat. So what we need is we need a vector for the boat and we need a vector for the current of the water so that we can add those together. So the boat is just heading north at 15 kilometers per hour. So let's say our boat vector, we'll denote that by b. This is going to be in the j direction, and we know its magnitude is 15. So that one's not so bad. Now the southeast one's a little trickier, so let's think about how that's going to work. So now I want my vector to be going in this direction, say, but I want it to have magnitude 7. So let's find a unit vector in this direction first. So this is I over 4 here. So a vector in that direction, if we don't worry about the length yet, could be I minus j. That would go 1 in the I direction and -1 in the j direction. But now I want this to be a unit vector, so let's divide this by the length, which is square root of 2. So this is a unit vector in the direction of the water. And now to make it length 7, we'll just scale this by 7. So that gives us our vector in the direction for the w. And so the vector representing the actual motion of the boat is going to be b plus w. So this is 7 over square root of 2I plus 15 minus 7 over square root of 2j. And this is measured in kilometers per hour. So that's our first thing. And then we could ask, how fast is the boat going relative to the ground? So this has to take into account both. So this is the magnitude of the vector u. So this should be magnitude u, which is square root of 7 over square root of 2 squared plus 15 minus 7 over square root of 2 squared, which is about 11.2 kilometers per hour. And finally, our last problem here, let's go to the next page. Okay, so the boat's trying to head due north, but that current's pushing it towards the southeast. So we want to say, what is the angle that will happen from that? So remember, we're looking at the boat plus the current. So we want this u vector, which was 7 square root of 2 over 2. If we clear the square root of 2's, I guess we can just leave it. We had it. So I say, what is the angle from this from due north? So if we were drawing this, we have this vector, something like this. And what we're interested in is, what is this angle here? Well, I know that this distance from here to here is 7 over square root of 2. And this distance from here to here is 15 minus 7 over square root of 2. So if I draw this triangle over here to the side, the opposite of this is 7 over square root of 2, and the adjacent is 15 minus 7 over square root of 2. So the angle then should be tangent of theta, should be the opposite over the adjacent. So this is about 4.95 over 10.05. And so we want arctangent of that. So theta is about arctangent of, and this is about 0.456 radians, or about 26 degrees. So it pushes about 26 degrees off from due north. Okay, so that's our introduction to vectors. In the next lecture, we're going to talk about some products. Notice that we added and subtracted vectors and we multiplied by scalars, but we didn't multiply vectors. And so it's a natural question to say, why didn't we multiply vectors, and what would that mean? So we'll address that in the next lecture.